Alrighty. So we are going to finish up our unit, Unit 10, on simple harmonic motion or periodic motion. So just a review of simple harmonic motion. Basically, you have a system where there's a restoring force proportional to its displacement. So the further you stretch something out, the more force is exerted on the object so that it goes back to equilibrium, like a spring. Right, the further you stretch out the spring, the more force it has and the more it wants to go back to its equilibrium point. Another system that is simple harmonic motion that exhibits simple harmonic motion is a pendulum, right? The more you displace it from its original equilibrium point, the more force it has and the more it wants to kind of swing down or swing back to its to its equilibrium point. So for a spring, right? We talked about in each of these harmonic oscillators, right? We looked at these in terms of energy. And so for a spring system, basically if you stretch out an object on a spring, it starts with some kind of elastic potential energy, 1/2 kx squared. And then as you let go, that elastic potential energy is going to become kinetic energy, or 1/2 mv squared, and then back to elastic potential energy at the other amplitude. Okay. And for a pendulum, right, we said that for a pendulum, the energy that it has when you pull that pendulum up a certain displacement, we said that that pendulum has some potential energy, or gravitational potential energy, or just mgh. And as you let it drop, that gravitational potential energy turns into kinetic energy, and then back to gravitational potential energy on the other amplitude or the other height that it reaches on the other side. Okay, so here's the big question, right? So these are all cool and all. Do these systems in real life, if you let the pendulum go, do they last forever? For example, if you have a child on a swing that's swinging, actually that's not a good example. Just let's say you have a bob on a string attached to the ceiling, just like we had, or a weight attached to the ceiling, just like we had in the last lab before you went on spring break, and you just let it go. It's gonna swing for a long time, but eventually, what's gonna happen? Well, it's going to reach a lower height or lower amplitude, and then as time goes on, it's gonna swing less and less until it stops. Right, same with the spring. If you have a spring system, when we did the lab previous to the pendulum lab, a lot of you had fun seeing the pendulums go up and down and just like wondering how long it goes on for. Well, it will go on for a long time, but eventually it will stop. And so what we call these systems, basically these systems are losing energy, right? So they're losing energy to friction with the air resistance, friction of the material. So like if you have the string attached to the ceiling, right, every time that string moves, it rubs against the ceiling, and so there's some energy lost through friction that way, etc. and etc. When these systems lose energy, we call it damping. So we'll talk all about damping when an oscillating system loses mechanical energy over time. Okay. We call these systems damped harmonic oscillators. That was not good. Okay. So a graph of this, an energy versus time graph of this, would look something like this. So let's say you have energy on the y-axis and time on the x-axis. Well, maybe you start with a certain amount of joules and a damped. Let me make this have a period of, there we go. Like that. That. Etc. Like that. So I'm just going to make it this. Okay, I like something like that. Okay, so you have an energy for static curve. It starts off with its maximum energy at t equals 0, and over time it loses energy. Eventually it goes to 0. The energy goes to 0. Now, one example of this might be of a kind of question you might be asked is, let's say you have a spring. So you have a spring, and instead of having an energy versus time axis, you might be given just the displacement, delta x, of the spring, and you're given that the keg value of the spring is 100 newtons per meter. Well, let's say you start from a displacement of, I don't know, 4 meters, and I ask you basically in this graph, how much energy has it lost in one cycle? Well, in order to find how much energy it's lost, first you need to find how much energy it has at the beginning and end of one cycle, right? So the energy it has at one cycle, well, we know the elastic potential energy is 1/2 times 100 times 4 squared. And the energy, that's the initial elastic potential energy. And the final elastic potential energy is, well, this is the initial and this is the final. So it's 1/2 times, well, now it's half, so it's 2. Well, it's the K is 100, but now the displacement is 2 squared. And so you end up that the difference is, well, this ends up being 4 squared, which is 16. So 1600 is 1600 divided by 2 is 800 newtons. Well, this is 4 halved 200 newtons. So it's lost 600 newtons. So 600, well, it's not 600 newtons. These are in joules because it's energy. 600 joules are lost. Okay, so that's a question you might be asked in mastering, on the upcoming test, etc. Okay. And the other system that you might be asked about is, well, the only other system you talked about is a pendulum. So let's say you have a pendulum, and that pendulum is on a ceiling. And it starts off at 10 degrees. And after a certain amount of time, so theta initial is 10 degrees. And after a certain amount of time, you end up with a pendulum that, like, I don't know, 10 seconds later, let's say 10 seconds later, it ends up with an amplitude of 6 degrees. Okay, and we know that the length of this pendulum is, let's say, 10 meters. Pretty long pendulum for some reason. Okay, well, how would we go about finding the amount of energy lost or how much damping there has been in this system, well, you would find the GPE at this point at 10 degrees, and then you'd have to find the GPE of it at 6 degrees, GPE final. And the way you'd find that is, well, you have to find the comparative height lost, and then you can just use that. So the change in GPE is GPE final minus GPE initial, which is just mgh final minus mgh initial, which is just mg times change in h. And you can find that change in h here by using some trig. You've got right triangles. You know the length of the length of the pendulum is. It's gonna write in blue. The vertical line is. You know the length of the pendulum is like that. Something like that. That would be L, and that would be L. So you have a right triangle with two sides and an angle, so you should be able to use SOHCAHTOA to find that vertical height. Okay, and that's how you find the change in potential energy there, which is basically just how much energy has been lost in your system. Okay, and again, damping occurs when there's friction usually involved in the system. Sometimes you can actually physically damp something, like a good example is like a kid on a swing, right? The kid on the swing, if he doesn't swing his legs or anything, he's gonna eventually slow down because of friction. But you could also slow him down because you're like actually pushing him when it comes into you. So you just like are physically slowing him down with a force because you've done some negative work onto him. So that's another way that you might damp a system, is if you're physically, mechanically just like pushing it as it goes into you. So you stop it, so you reduce its amplitude every time. Okay, so that's basically damping in a nutshell. If you have any questions, you can just message me on Google Hangouts or arrange a time to meet you can book me so we can talk through Zoom. Okay, yeah, good luck, and I'll see you soon.